Well, folks, hello there, and let's do a very quick review of IM forces. In fact, I don't even like to call these IM forces because it's not just IM forces. These are really interparticle forces is the way I think of them because they don't have to be between molecules necessarily, as you'll see in a while. Well, first, let's start with London. What are London? Hey, London forces are induced dipole forces caused by the random motion of electrons. And these random motion of electrons cause temporary dipoles. And what I mean by that, let's say we have something that has 3 protons and has 3 electrons, right? And we usually will think of the electrons being spread out somehow, right? But it's possible that these electrons, by random motion, kind of end up all on the same size. So what does that make for my molecule? That makes this side partially negative and this side partially positive, and so that's how we can get a dipole formed. And then if I had another one of those same molecules next to it, then, or atoms next to it, or molecules, then what would happen? Then I would get a partially positive and partially negative, and I get an attraction between the negative on this one molecule and the positive on this molecule, and then I would have a London dispersion force, right? Now, these can be very strong. The strength of London forces depend on 2 things. Number one, polarizability. Good. What is polarizability? It is the ability to distort from an electron standpoint. Well, we'll just call it distort the electron cloud. Good. And polarizability increases as the number of electrons increase. So the strength of my London forces increases with the strength. So my London dispersion strength increases as the number of electrons increases. And that is why, for instance, I2 is solid, whereas Br2 is a liquid, and what? F2 is a gas. These all have just London forces, but this has a lot of electrons, so it's very polarizable. That means it has very strong intermolecular forces, and it can be a solid at room temperature, where bromine is a liquid and fluorine is a gas. The other thing that affects my strength of London forces is really the shape. Compact shape versus elongated or flat. And the elongated shape will have stronger, higher London forces, and mainly because you have, if I have 2 shapes that are long like this, right, there is a lot of area here where I can have an interaction between my molecules. So there are more points of contact as opposed to compact um, molecules where you only have a few points of contact at which the London forces could uh, occur. So elongated or flat molecules have higher London forces than compact molecules. Good. Now, before I go too far, I should probably talk about the most important equation that in discussing IM forces, and that is our Coulomb's law, right? Coulomb's law says my force of attraction is K Q1 Q2 over R squared. Now, what are my, this is what? This force represents the force between a positive and a negative, or a positive and a positive. In this case, we're looking at a positive and a positive on one molecule and a negative on another, or a positive on one particle and a negative on the other. Q1 we can think of as the charge of my positive dipole. Q2 can be the charge of my negative, the strength of the charge of my negative dipole, and R is my distance between them. So if I have 2 entities, and I have a, let's say we have a +1 here and a -1 here, and their R is this far apart, and I have another entity, and here's a +2, and here's a -2, and here's their R. My Q1 and Q2 are bigger. My R here is smaller. So that would mean my force of attraction, this is what? Denominator. These guys are numerator. So my force of attraction between these two is far greater than it is between those. Got it? And that's how we should think of this in terms of our coulombs. I mean, in terms of IM forces. Why is it that if I have why are my London forces stronger if I have more polarizability? If it's more polarizable, my partial positive is bigger, my partial negative is bigger, meaning both my Q1 and Q2 are bigger when I have a very polarizable cloud, which means my force of attraction in my London forces is bigger. Good. Dipole-dipole. What is dipole-dipole? That's a force of attraction between, this is between the positive pole on a polar molecule, the positive pole on one polar molecule, and the negative pole on another polar molecule. So I can have something like HCl and another HCl. If you know HCl, right, we know that the electrons are closer to the chlorine than they are to the hydrogen. So that's a partial positive. This is a partial negative. So here's a partial positive side. Here's a partial negative, partial negative, partial positive. And the attraction right here is my dipole-dipole attraction. Got it? So the first thing I have to have for a dipole-dipole attraction are two polar molecules. Got it? Good. Now let's talk about the strength. Two things affect the strength of my dipole-dipole. Number one, the strength of the dipole moment. Dipole moment. Now, what is a dipole moment? That's just a measurement of this positive, partial positive to partial negative. The bigger that difference is, that would indicate the stronger my dipole moment is. And really, that would mean what? My Q1 is getting bigger as this dipole moment gets bigger. Q1 and Q2, excuse me. Good. And then the other thing that affects my strength is the distance. So for very strong dipole-dipole moments, we want, and distance, a surrogate for distance, is the size of my molecules. So for me to have very strong dipole-dipole, what do I want? I want a strong or a big dipole moment and small molecules. So I want their size to be small so they can get close to each other, and I want the dipole moment to be big. Got it? All right, so that gives us an idea of dipole-dipole. Now, the key question on dipole-dipole is whether a molecule is polar or not. How do we know that? Here's the basic decision-making process. Number one, we have to look at shape. So the first question is what kind of shape? And is it asymmetric? If it is asymmetric, then it is polar. Asymmetric, that means it is polar. That's simple. If it is symmetric, it's not that simple. We have to ask ourselves another question. Is it symmetric? Yes. Do all atoms surrounding the center have, all atoms surrounding my central atom, do all atoms have the same electronegativity? And if the answer to that is yes, then it is nonpolar. If the answer to that is no, then it is polar. Now, folks, what's the easiest thing we can assume? Hey, very few of our atoms have the same electronegativity. So a rule of thumb, if my central atom is not surrounded by the same atoms, then we can assume most of the time that it's going to be polar. For instance, here we have CH4. That means I have, let's draw this in a different way. We have CH4, right? It's a tetrahedral. Good. That is a symmetric shape. All my atoms around my central atom are the same, so it is nonpolar. But if I have Cl, Cl. Then I have two atoms which are not the same as the other, and although this is a tetrahedral, which is a symmetric shape, since I don't have the same thing surrounding it, this would be a polar molecule. Now the question is, what shapes are symmetric and what shapes are not? Asymmetric. Okay, bent is asymmetric. Trigonal pyramidal is asymmetric. Seesaw, T-shaped. What else do we have that's asymmetric? Square pyramidal. Got it? Those things are all, what is this? This is a 2-2, this is a 3-1, this is a 4-1, this is a 3-2, and this is a 5-1, right? All of those are asymmetric shapes. What are my symmetric shapes? What are my symmetric shapes? Linear, trigonoplanar, tetrahedral, trigonal, bipyramidal, octahedral, square, planar. All of these are my symmetric shapes. Got it? Good. Moving on. Hydrogen bonding. What is hydrogen bonding? Hydrogen bonding is a special type of dipole-dipole, and what we have to have is a hydrogen bonded to a fluorine, or a hydrogen bonded to an oxygen, and a hydrogen bonded to a nitrogen, and an unshared pair on something out there. If I have those situations, I can have hydrogen bonding. So let's take let's say we have, well, first let's show it here with HF. So I have HF, right? And I have some unshared pairs, and I have another HF here and some unshared pairs. And where is my hydrogen bonding? It is right here. This is my partial positive, this is partial negative. And so my hydrogen bonding is between the unshared pair on one molecule and the hydrogen on the other, right? Now, I don't have to have the same situation. I can have I can have an oxygen hooked onto some kind of organic molecule, and it has a couple of unshared pairs, and then I can have something like water, which can form hydrogen bonding with this other molecule as long as it has an unshared pair that is reachable by my hydrogen, and my hydrogen is bonded to an oxygen, fluorine, or a nitrogen, right? So that is a hydrogen bonding. Now, what makes hydrogen bonding so strong? Well, mainly is my R gets very small in these molecules. Because of the strength of my electronegativity of the fluorine, for instance, hydrogen is essentially a naked proton. Ooh, naked proton. And that naked proton has very small size, and so it can approach this molecule very close, so my R gets very small. And remember, force is equal to K Q1 Q2 over R squared. As that R gets very, very small, what happens with this force? It becomes very, very strong. Okay? Good. So that's hydrogen bonding. Ion dipole bonding, what is that? That would be something like sodium, cation, and chloride, right? And they are attracted to what? Water. So in my water, what side of my water is going to be attracted to my sodium? Well, the partial negative side with the unshared pairs. So here, this attraction between my ion and my dipole molecule would be an ion dipole molecule. And what does the strength of that depend on? It's going to depend on the charge of my ion, the dipole moment, as well as what? R, the size. So the bigger my charge, the bigger my dipole moment, the smaller my size, the greater my force of attraction. Okay, good. Now, where does this all lead to? It leads to IM, forces, and states. The major idea is, what I always think is there's a competition between my IM forces and average kinetic energy, right? In the determination of states. So if we're at any temperature, ion forces and the state have a direct relationship. The stronger the ion forces, the more likely that it's going to be a solid at a given temperature. Or to state it another way, as ion forces increase, my boiling point is going to increase, and generally my melting point increases. So when I have a very strong intermolecular forces, I have high melting point, which indicates that at room temperature, that is probably a solid. And if I have low ion forces, that means I have a low melting point, which means at room temperature, that's probably a gas. Got it? Okay, so that's my relationship between ion forces and states. One other one that shows up now is ion forces and vapor pressure. If you remember, in vapor pressure, you have a closed container with a liquid in it, and you have some of these at a certain temperature, and you have some of these particles which have enough kinetic energy to be in the gas phase, and eventually you have an equilibrium formed between the gases going into liquid and the liquid going into gases, and that pressure is our vapor pressure. So now, do I have a high vapor pressure? When these are very strong forces, what does that indicate? Do I have a lot of vapor or a little vapor? If I have a strong ion forces, then my vapor pressure is going to be low. And if I have low ion forces, then my vapor pressure is going to be high, because if my ion forces are low, that means there's at any given temperature, it's relatively easy for my liquid to be in the gas phase. And if I have a lot of stuff in the gas phase, then I have a high vapor pressure. Good. One other thing that's related to this are heating curves. So let's talk real briefly about heating. This is almost what heating curves are, really a form of thermochem. But if we have a heating curve, right? We have a heating curve, looks something like this: yoink, 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 yoink. And let's just take water, but no, we can take anything. This line right here is going to represent the melting point. This line right here is going to represent the boiling point. This is temp, and this is heat added, right? And so this is going to be my solid area. This is going to be my liquid area, and this is going to be my gas area. And this area is going to represent what? Fusion. In this direction, and in this direction, it's going to represent freezing. And this is going to represent what? Vaporization. And in this direction, condensation, right? Good. And so that's our vapor pressure, our vapor, that's our heating curve. And we really have 5 different calculations here. In my solid, it would be Q solid equals M solid, C sub P solid, delta T solid. Here it's Q liquid equals M liquid, C sub P liquid, delta T liquid. And here Q gas equals M gas, C sub P gas, delta T gas. And here we have to look at our latent heats, and that's usually, you have to be careful, we'll look for units, moles times your delta H vaporization. And here it would be moles, so this is my Q vapor, and this would be my Q fusion, which would be moles times my delta H fusion. And so you add all those together, watch your units, because quite often this is in kilojoules and quite often this is in joules. So you have to make sure that your units work out. And there's always the relationship, what? That delta H vapor is equal to in magnitude to delta H condensation, except for you have a different sign. And delta H fusion is equal to delta H freezing, except for different sides, right? One other final thing, right? Fusion is what? Endothermic. Everything going up is endothermic. Vaporization is endothermic. Condensation is exothermic. And the coolest thing is freezing is what? Exothermic. That means when you're really cold outside, just take a big old vat of water and let it freeze. And as it freezes, you can sit there and get your hands warm, right? Good, because while this water freezes, it will release energy. Wow. All right, what else do we have here? Phase diagrams. This is not on the AP exam, but phase diagrams are a nice thing to know. What do we have here? you have temp and pressure, and goes something like, nope, that's pressure and temp, I think, right? And it goes something like this, something like that. Did I increase my pressure? Yes, that's right. This would be a solid region. This would be a liquid region, and this is my gas. This point right here is triple point, and at that point I have an equilibrium between solid, liquid, and gas at my triple point. Up here somewhere I have something called what? My critical point. My critical point, which is my critical temp and my critical pressure. And all you have to, this kind of way to read this is, the question might be, I start here at this pressure and I increase temp. What happens? Well, I go from a solid directly into my gas phase. And so what does this line here represent? That line represents what? Sublimation. And so I could say that my solid sublimes at this point, and I could read that temperature at which it sublimes. If I'm at a higher pressure, I go from a solid to a liquid. So what is this point right there? That's my melting point. And then I go from a liquid to a gas right here. So that would be my boiling point, right? Good. On this line, what do I have? I have an equilibrium between a liquid and a solid. On this line, what's going on? I have an equilibrium between a gas and a liquid. And at this point, I have an equilibrium between gas, solid, and liquid. And what do I have up here? Who knows, right? It's what? It's critical. It's a supercritical fluid. Good. Above my critical temp, I cannot have a liquid, right? And the pressure at which the top pressure at which I can no longer have a liquid is my critical pressure. Okay, I think that is good enough for now. Like I say, this stuff won't show up on the AP exam. It may show up on your SAT science, your SAT chemistry. So it's good to know, and these things are easy to read. Okay, that should be it. I hope they helped. All right, good luck on the AP exam. Bye.